Welcome back to the NASA Citizen Science Community Workshop Series. I'm your host, Sarah Kirn from the Gulf of Maine Research Institute. It's hard to believe we've come to the end of this summer series, and I am so pleased that this event today is only an end to this first chapter in our conversation. As we announced last time, NASA has chosen to extend this series for the next 18 months. We're going to take a short breather to plan and regroup. Please send in your surveys to have a say in what we do next. Let's get on with today's program. As always, we'll start with reminders. Please use the chat and introduce yourselves if you've not done so already. And if you find that chat distracting, you can close it or move it aside. Note that the chat default is to send your chats to panelists only. When you write a chat note, use the blue box just above where you type to redirect your comments where you'd like them to go. Please use the Q&A tool, which you'll find in the footer next to the chat tool, to submit questions for our speaker. You can vote for questions in the Q&A tool and comment on them. If a question seems to vanish, look at the top of the Q&A window for the tabs to access answered questions. It's probably there. As usual, we'll begin with a conversation. So once again, I'm here with Dr. Marc Kuchner. Thank you for joining me. So this is truly the bonus finale event of the first part of this series, and also maybe the kickoff of the second part of the series all in one. But I wanted to ask you if you, I'm so excited. I hope everybody else is as excited as we are. I wanted to ask you, do you have any big takeaways from the first, from the summer?
There were so many. You know, I think I learned a lot about, what we need to do to broaden participation in science, in citizen science. I think I learned a lot about how we can interact better with our citizen scientists and what kinds of support our scientists need go forward. I'm just so pleased to have the whole gang together during these difficult times. I'm so glad we'll be able to continue.
I am too. Yeah, and you touched on some of the really big themes of this summer, and the events that we had were so exciting, and we had some great speakers, and it still feels like we just scratched the surface. And there's quite a lot to be done to take those ideas and really figure out how to use them effectively in projects. And one of the things I'm most excited about for the future parts of this series are the workshops that we're planning that will really bring people together in small groups and get down to ground. Like, how do we take these big ideas that we heard and figure out what do they look like in projects and what might they do to help projects be successful, recruiting and retaining and engaging people, and making more scientific discoveries in NASA citizen science.
I can't wait to see how the Catalina Outer Solar System Survey has been doing, and the NEMONET project and the Planet Patrol project, all bringing us new insights, new science. I hope we'll get to hear from them soon. That's first one. How about you, Sarah?
I think that would be great. I've had so much fun learning more about NASA citizen science, and I have a background in oceanography. I haven't studied the stars, so I'm learning a lot and having a wonderful time, and it's been really fun. So I'm just excited to be able to continue and to do more work with you in this community.
Super.
So today we have a really special opportunity. At the very start of this series, we started talking about who we wanted to invite to speak, and Andrew Westphal's name came up very early and very often. And today we get to see his keynote presentation. And hats off to Andrew, because we were originally planning to present his keynote on June 10th, and he was an enthusiastic supporter of our idea of setting that program aside and having the conversation around combating racism in citizen science and in science. And he even joined us for that day on June 10. And now, not only do we have a chance to bring his talk, which is so wonderful to this community, but we also have him with us here.
Sure. You know, I think Stardust at Home was really the time when NASA emerged into the citizen science field. I mean, we had Clickworkers before, which is a cool demonstration of, you know, the power of online crowdsourced data analysis, right? Stardust at Home was, you know, it was the inspiration for Zooniverse, right? It was the inspiration for Galaxy Zoo.
Yeah.
So that was when we started driving the bus in terms of NASA science, and it was Andrew's idea. And Andrew's very modest about it. He talks about how they discovered these interstellar dust grains. I want to point out that these are the only samples of interstellar dust grains. So there are only 8 of them. They're precious. These are the only ones that exist. And his idea to dig this out of these samples, it's a whole new kind of way of learning about what's out there beyond the solar system, and it wouldn't happen without this project. So keep
Yeah.
all those things in mind as you listen to his modest presentation about the amazing things that he and his group have achieved.
Absolutely. And I think more than anything else over the summer, Andrew is really the one who, this Stardust at Home project in so many ways epitomizes the opportunity that NASA citizen science offers the public, which is to be a participant in this kind of discovery about things that we don't know. And I think it's inspiring. Well, then without further ado, let's let Andrew take the stage. Thanks so much.
All right, well, thank you, Sarah, for that introduction. So I'd like to tell you about our experience with Stardust at Home and the analysis of the first interstellar rocks in the laboratory. And this has been an enormous effort, so I'm just speaking on behalf of a huge collaboration. The local group here at Space Sciences Lab at UC Berkeley is here on this slide, but in fact, we have a collaboration of thousands of people. So more than 60 professional scientists who've been involved in this project, and more than 30,000 Stardust at Home volunteers. So I want to, before I talk about the citizen scientist part of this, I'd like to talk a little bit about the science behind it that really underlies the project and motivates it. So our group at SSL at UC Berkeley is fundamentally interested in understanding the earliest history of the solar system. So that time, about 4.5 billion years ago, when the sun, the planets, the asteroids, the comets were forming from a cloud of interstellar gas and interstellar, what astronomers call dust. I actually think of as rocks because that's really what they are. They're really tiny solid materials. And so one of the things we've learned from the Stardust mission is how complicated that early solar system really was. In some sense, we're a little bit like archaeologists. We're trying to understand this earliest history of the solar system based on the clues that are locked in the tiny, tiny samples that we've gotten from the Stardust mission and from other sources of extraterrestrial materials. And so, like archaeologists, we're trying to understand our own origins. It's not just the formation of the Earth and the planets and the sun, but it's really about understanding where we came from. And I'll get into that a little bit more in a minute. So that was a simulation that I just showed you, but lest you think that that's just some fanciful simulation, we actually see star systems forming right in front of our eyes. This is an image of a star system forming now in our galaxy called HH30. This was taken by the Hubble Space Telescope. More recently, we have now these fantastic images of protostellar disks, like this one, HL Tau. This is taken from the ALMA telescope in the Atacama Desert in Chile. So this is a protoplanetary disk with, we think, lanes which have been cleared by planets. This is much larger than our own solar system, in fact, and I've overlaid our own solar system for scale. The tiny little circle in the middle is the Earth's orbit, and the outer circle is the orbit of Pluto. So this is a large object, and I put this on here to place our own collections of extraterrestrial materials into context. So in the slide or the graph on the right, lower right, I'm plotting, I'm summarizing our collections of extraterrestrial materials that tell us about the early history of the solar system. So we have thousands of kilograms of meteorites that have fallen to Earth, first recognized in the late 18th century. And that's told us a lot about the formation of the solar system. We also have more than 300 kilograms of materials from the moon that were brought back by Apollo, and a little bit from a Soviet mission called Luna. We have samples of the sun that were recovered by the Genesis mission, the NASA discovery mission called Genesis. And we have samples from an asteroid from the Japanese mission called Hayabusa. And we expect to have very soon materials from two asteroids, one from a follow-up mission called Hayabusa 2 from the Japanese Space Agency, and a NASA mission called OSIRIS-REx. But one of the things that's really clear, if we want to understand everything about the early solar system, is we have to sample not just from the inner solar system, which is where those materials come from, but from throughout the entire disk. And that really means that we have to have samples from the Kuiper Belt, and that means samples of comets. And we also need samples of material from outside the solar system. So in particular, interstellar rocks. And that's what I'm going to be talking about. And that was the focus of the Stardust at Home project. So it turns out that more than 99% of small bodies in the solar system are actually objects from the Kuiper Belt. But what that means is that we have such tiny samples from comets that they're underrepresented in our sample collections by about 13 orders of magnitude. And it's much worse for the interstellar materials. So interstellar materials, as I'll talk about, are incredibly rare and precious. So this is a kind of summary of where we are to emphasize the point that we're really in a golden age of sample return. Beginning 50 years ago with Apollo missions, but recently in the last 20 years, starting with the Genesis mission, which returned samples from the sun, the Stardust mission, which was really two missions in one spacecraft to return material from a comet, and also interstellar materials, and then the other missions that I've talked about. And we're excited that this golden age is going to continue, and that we're going to be looking at more materials from throughout the solar system as NASA and other agencies do their planning for the next decade and more. So we have samples from all over the solar system. We have samples from the sun all the way out to the edge, to the Kuiper Belt and now beyond. But really, I think the point I want to make here is not so much that we have these samples in our hands, because having the samples is only the first step. The second step is really to be able to analyze them. And these are really challenging samples. And so we have, as it turns out, an increasingly sophisticated suite of analytical instruments in the laboratory, from electron and ion microscopes to X-ray microprobes. I'll talk about that in more detail in a bit. Ion microprobes and mass spectrometers, which can analyze these incredibly complicated samples, and they're complicated on a tiny scale. So having these in our hands is really essential to being able to do the work we do. And in addition to that, and maybe this is only interesting to those of us in the business really, are the increasingly sophisticated techniques for preparing these samples to get them into the instruments, because that in itself is a real challenge and is a lot of fun, and is all just enormously challenging in a lot of ways. So what we're trying to understand really is, how do we get from stars to us? So the solid materials, what astronomers call dust, and again, I'll call them rocks because that's really what they are, came from other stars and from circumstellar outflows, and went into the so-called ISM, the interstellar medium. These materials then formed disks like HL Tau and other things that we're looking at now with a lot of excitement. And then these went in our solar system into comets, asteroids, and differentiated bodies like Ceres and Vesta and the Sun, and the Earth and other planets. So we really spend most of our time studying samples returned by the Stardust mission. So Stardust was a NASA Discovery class mission that launched in 1999. It was 2 missions in 1 spacecraft. And what you can see here is that sort of disc-like thing sticking up at the top is a 2-sided collector. The front side collected cometary material by flying through the coma of a Jupiter family comet called VILD-2. It flew past VILD-2 at 6 kilometers per second and collected material, about 300 micrograms of material from the comet in aerogel and aluminum foils. The backside, and I'll go back to that, the backside collector was exposed to interstellar dust, and I'll talk about that more in a minute. So Stardust came back to Earth in January 2006 to the Dugway Proving Grounds in Utah with a record high reentry speed, so it was quite a dramatic thing. I and my family were one of the few, I think, who were fortunate enough to actually see it. It came back in a blizzard, but we happened to be in just the right place where we could see it come in. It was an amazing experience. And then we at SSL at UC Berkeley developed the techniques which really enabled us to extract the particles from the aerogel collectors. And this is one of the very first little tiny so-called keystones that we extracted from an aerogel collector in 2006 containing a cometary particle. And this is what this looks like. So here's a cometary particle that was captured in aerogel, extracted in one of these little wedge-shaped pieces of aerogel. And these particles were so fragile that they broke up into lots of little pieces. And so what you see is this sort of characteristic ginseng-shaped track with a bulb at the top. The particle came into the aerogel from the upper right and then broke up into lots of little pieces, each one of which is a fascinating rock. And I will give you an example. So this is a particle called Iris. It was named by my youngest daughter when she was about 6, and she spoke Spanish. She saw that and she saw, oh, that looks like a rainbow, Edith. And so so Iris is something we studied extensively. It's a 15 micron particle, very complicated, and it turns out to be a tiny little a melt object, like an igneous rock. And so we were able to analyze this first on a synchrotron using an X-ray microprobe, and then we used a diamond knife to cut it into really tiny slices and do analysis on it. I don't have time to talk about all the various things we did on it, but we spent several years on this one tiny little particle that's only a tenth in its biggest dimension. It's only a tenth as big as a human hair, and incredibly complicated little thing. And it turned out that the analysis of this particle, Iris, told us about the timing of the formation of the planet Jupiter. So here's this tiny little thing that's telling us about the formation of the largest planet in the solar system. So this is just an illustration of the incredible information that we have the tools now to be able to unlock, the secrets from these little samples. So now I want to turn to the interstellar dust collection, and the interstellar dust was collected during 2 phases of the Stardust mission before the encounter with the comet, in which the spacecraft happened to be going in the same direction as a stream of interstellar dust that's coming into the solar system at all times. We had to develop new techniques to be able to analyze these particles because they're so tiny, and the techniques that we require very specific conditions and analytical techniques. So we developed this technique borrowed from microbiologists largely to extract these tracks from the aerogel tiles in so-called pico keystones. So these again are these little tiny wedge-shaped pieces of aerogel, but much more sophisticated, much more difficult to make, much more challenging, but they worked great in the end. And so when we got the cometary samples back, we thought these are the most challenging extraterrestrial samples ever returned. Compared to meteorites, compared to a lot of other things, these are really hard because they're particles that are embedded deep in aerogel. Just being able to do the microsurgery to be able to get them out is hard, but all the analytical techniques that we want to apply are just doubly, triply, quadruply challenging. But it turns out that the cometary samples are easy by comparison with the interstellar samples. So the typical interstellar particle is 1,000 times smaller than the typical cometary particle, and we have less than 1% as many of them. We have thousands of particles from the comet. We probably only have a dozen or a couple dozen particles from the interstellar collection. So these are by far the rarest sample collection that NASA curates in JSC in Houston, where all the extraterrestrial materials are curated. Right after the Stardust mission came back, we started something called the Interstellar Preliminary Examination. This was, I think, the 5th PE, so-called preliminary examination that was conducted by NASA. The first one was from Apollo, unsurprisingly. And the Stardust ISPE consisted of 6 related and coordinated projects. So the first step was to scan the aerogel collectors to identify impacts in the collectors that could be interstellar dust particles. And it turned out that we already had in our group at Berkeley an automated microscope that we had developed for a completely different project, a cosmic ray instrument that flew on the Russian space station, it turned out. We could adapt that for automatically scanning the aerogel. And then we needed to identify the tracks visually to find candidates. The second step is to extract those particles from the aerogel using these tools borrowed from microbiologists. Then we do analyses on these using synchrotrons principally, so X-ray and infrared microscopes at synchrotrons. So synchrotrons are basically giant X-ray microscopes the size of shopping malls, and something you could never ever hope to fly in space. And so this is an illustration of the advantage of sample return. You can bring these samples back and analyze them using instruments that you would never be able to fly in space in any practical way. So we used the advanced light source, which we were very fortunate is only a 4-minute drive from our lab at Lawrence Berkeley National Lab. But we also used synchrotrons around the world. And I'll come back to that actually in a bit. So about 85% of the collecting area of the Stardust Interstellar Collector was aerogel, but about 15% was aluminum foil. And that turned out also to be really valuable for collecting interstellar dust. And so we had a parallel effort led by Rhonda Stroud at Naval Research Lab to identify craters in the aluminum foils and to analyze them. And then we had 2 supporting projects to carry out a campaign of laboratory shots to understand and calibrate the images or the morphology of the tracks that we saw in aerogel and foils to be able to constrain, for example, the velocities of the particles as they come in. And then we also had a project to understand the propagation of interstellar dust in the heliosphere, which turns out to be really complicated. And if anything, this is already hard enough, but this makes it even harder to analyze what we saw and we had to take into account the propagation of interstellar dust in everything we did. So when we first got the samples back in 2006, and we started to think about how were we going to find these interstellar dust tracks in aerogel. That was what we were focused on principally at first. We assumed that we would take an approach in which we would use some sort of automated technique for identifying the tracks. And we're fortunate here at Berkeley to have a bunch of experts, even then, who were really interested in automated image recognition. Those were in the early days of machine learning and automated object recognition. So we went and consulted with them, and we learned a bunch about what the state of technology was. And there were some examples. This is one in which they were trying to automatically recognize characters in images that are deliberately distorted, maybe fragments of characters and so on. And so this is a relatively easy task. Another one was application of machine learning and automated image recognition to pornography detection online for protect children. And this is a paper showing some false positives of automatic detection of human nudes. Clearly these were, not working very well. And so, this was in the early days when things really weren't really very sophisticated yet. And so we realized that machine learning and automated techniques were not going to work. But what we did know and notice was that whenever we had a visitor to our lab, maybe somebody who'd never looked in a microscope before, and showed them a track of a particle in aerogel, even somebody who'd never, was totally naive, never had seen anything like this, could very instantly detect this trap. And so we thought, aha, what we can do is ask for help with people who are out in the world and interested in helping out. And so that's what we did. And but we were really worried, about this idea of bringing in people who have, are going to make mistakes, who we've never met before, so we know nothing about how sophisticated they are. But we took inspiration from a very famous physics experiment called Super Kamiokande. So this is a giant underground particle detector. It consists of a giant tank of water, which is lined with light detectors called photomultiplier tubes, which are very sensitive. They can detect single photons, but they're very, very noisy. So even when there's no light around, they're always firing all the time at a huge rate, 100,000 times a second, each one of these detectors. But by combining the data from more than 10,000 of these photomultiplier tubes, this detector can detect the passage of single particles, muons and electrons, at essentially 100% efficiency with no false positives. And so what you're doing is you're leveraging many observations to be able to make a really sophisticated and very efficient detector. And so that was the approach we took with Stardust at Home. So the idea was to recruit people from around the world to help us to look at so-called focus movies. These are stacks of images that are taken as you focus down through the aerogel. The aerogel's transparent, fortunately, and so you can see tracks within the aerogel. And so you can use the little focus feature on the side in the tool to focus up and down, just as if you were looking through a real microscope and turning the focus knob yourself. And you can look up and down and to look for these tracks. This has now been running for, I guess, 14 years now. We've had more than 35,000 volunteers. They've called themselves dusters. And collectively, they've carried out about more than 130 million searches of the fields of view in these tiny little microscopic images of the collector. And I should say something else that I forgot to mention earlier. When we were first thinking about this, we realized, when we thought, well, okay, maybe we can't get machine learning to do it, but maybe we can do it ourselves. This is something maybe we could do. But if you do the math, it turns out you have to search about 1 million fields of view. And we did the math and realized it would take us more than a century to search these things ourselves. So that's why we needed the help. And so we've discovered through this process more than 200 tracks in the aerogel. And now we've extended this to searching for craters and foils as well. So speaking of that, this gives an illustration of the challenge of finding craters in these foils. The foils were not actually intended for a collecting medium. It turned out they were really important, but they were actually only installed on the spacecraft as a way to get the aerogel out of the frame. But it turns out to be really important. But they weren't intended as a collecting medium, so they have scratches, and if we were going to do it again, we would do it differently. But to find a crater in the middle of all of this is really hard, but people can do it, and people can do it really efficiently. So this was one of the things that really got our attention when we first started up, and we had a lot of interest. We didn't ever have to do any advertising. for this because Stardust was already in the news and people were really interested in participating. And so we had a huge amount of interest, crashed our servers. You know, it was one of those things. We didn't expect anything like that, but we got a huge amount of data to analyze. And one of the things that we put into the stream was the calibrations, which enabled us to do all kinds of important things. And it was really essential to the approach. And these calibration images, these were images that we already knew the answer to, and they're injected into the stream of data for everybody, but nobody knows which are calibrations, which aren't. So in an analysis of 15 million calibration images in the first few months, what we found was that people were extremely efficient at finding these. So any track larger than about 5 microns, any individual person had more than 90% efficiency at finding that. But again, coming back to this idea of the super Kamiokande experiment, we could go all the way down to less than 2 micron tracks, because even if the probability of one person is only 60% of finding a track, by combining, let's say, 30 different observations, independent observations of the same field of view, looked at by 30 different pairs of eyes, you can raise that efficiency essentially to 100%. And so, so this was just for us very, very exciting, and an illustration of how the power of this technique. So here are some of the images of those tracks, and this really vividly illustrates the challenge. So some of these tracks, like the one that's down here at the lower right, that one's pretty clear. That's a long track. It turns out not to be interstellar. That's from an impact on the spacecraft, it turns out. But that's pretty easy. But some of these other tracks, boy, they're subtle. You know, they're really hard to find. And what we found is that our most dedicated dusters who have spent, huge amounts of time doing this work are actually much better at this than we are, which is maybe not too surprising, but very gratifying actually. So we analyzed, or we identified in the preliminary examination 71 tracks. And out of those, most of those were not interstellar. They didn't pass our criteria, but we did find 3 in the aerogel that passed all of our criteria for being interstellar dust. So the first one was called Orion. These are synchrotron X-ray analyses of Orion. There's a map on the left, which shows a magnesium, aluminum, and iron map in blue, green, and red. And it shows the tiny size of this particle. So in its biggest dimension, it's only 2 microns in size, and only less than a micron in its smallest dimension. We could also do X-ray spectroscopy on this particle, which told us about what minerals are present. So we could identify olivine and spinel, 2 fairly common minerals in the universe, but also an amorphous magnesium bearing phase that we still don't really understand. And the thing that was really puzzling is that the density of this thing is actually less than that of water, which is really still a surprise and something we don't understand. But it appears to be a kind of hollow object. We were also able to do at the synchrotron in Grenoble, France, the SREF, European Synchrotron Radiation Facility, we were able to do X-ray diffraction on this particle, and that confirmed a lot of the analyses that we did at the ALS. And I should say about Orion, by the way, that this was a particle not discovered by us. It was discovered by a guy named Bruce Hudson, who is a retired carpenter in Ontario, Canada. And so Bruce got his picture in Nature, and it was a great thing. So, and Bruce named the particle. That was one of the benefits, I guess, of being a discoverer, is that not only do you get to name the particle, you also get to be a co-author on any publications that come out. Second particle was called Hyllabrook. This was discovered by Naomi Wordsworth in the UK. And this is also has olivine in it, but it's very different. The X-ray spectroscopy shows that the amorphous magnesium bearing phase is quite different than it is from Orion. A lot of things that we still don't understand about these particles, but they're really quite different. So the diversity is large. The third one is track 40, and this is one that at such a high speed that it essentially totally vaporized. And so it was left, we don't know what the original particle looked like, except that we do know that it probably was pretty compact because of its high speed. And that's a story that I could get into if you'd like in questions and answers. And again, here's that same crater in foil. We found 4 craters that we identified as being of likely interstellar origin. And so we published these results in in Science in 2014. There's the list of all of the professional collaborators, and you also notice that there are 30,714 Stardust at Home dusters as co-authors. I was trained as a physicist, so the thing that was also gratifying about this was that this made the cover of Physics Today. So, so that was fun. So Stardust at Home was one of the earlier, not by no means the earliest, and I'll come back to that, but one of the early citizen science projects, and has inspired some others. But I think the one that is to me been the most gratifying is a project. It was initially called Eyes on ALZ, and now it's called Stall Catchers. And this is a project from Cornell and the Human Computation Institute to evaluate blood flow in living mouse brains. And this supports Alzheimer's disease research. So that particularly has a resonance for me because my dad died of Alzheimer's. And of course, Alzheimer's has touched so many people. Who could have known that, our interstellar dust project could have some bearing on Alzheimer's disease? You never know how these things go. It was something that was, I think, was inspired by our project. Uses a tool which is very much based on the tool that we developed at Berkeley for looking for interstellar dust. So I'd like to now talk a little bit about some of the lessons that we've learned from Stardust at Home and over the years. And there are a couple of things that I think are really relevant to this that I think may or may not be extensible to other projects, but they're unique characteristics of our particular project. So one of them is this, and this is a slide I showed before. So the Stardust project really is many projects that are coordinated to come to the answer at the end. And the Stardust at Home part is the critical first step, but it's only the first step. And as you make progress, as one makes progress in analyzing interstellar dust in the laboratory, the rate at which you can make progress is really determined by the slowest step in this entire chain. And it turns out that it's been true for the entire project that the citizen science part, the Stardust at Home part, has never been the bottleneck. It has been principally, largely, the analyses at synchrotrons, because the synchrotron microprobes that we use are heavily oversubscribed. They're the most sophisticated ones in the world. The one that we used for the ISPE, for example, is oversubscribed by a factor of 5. That is to say that if you write a proposal to get time on that beamline, it's kind of like proposing to get telescope time on a big telescope, only about 20% of proposals are accepted. Now, we've done much better than that, but it is still true that the beam time is very, very limited. And there may be, if a track is identified, it might be years before we can actually analyze it. And we're also faced with the problem that most of the tracks that we analyze are not interstellar. They are from other sources, principally from impacts on the spacecraft. And so that means that it's a challenge which we've never really solved, which is that, and I understand the frustration of volunteers. I found this track and can't you tell me the answer? And the answer is you'll have to be patient because you're way faster than we are just by the nature of what we're doing. And so that's been an ongoing challenge. And I think maybe that's a little different than some citizen scientist projects where most of the work is done by citizen scientists. And here it's a critical part of it, but it's not everything, or even the majority of it. So I think the way I like to think about this is, when I think about Stardust at Home, is I think about one of my favorite places in the world, which is Chartres Cathedral outside of Paris, which took 150 years to build. So the people who started shot. The masons and the architects started the project knowing full well that they would not live to see it. And in fact, it would be generations of effort required to finish Chartres. And in some sense, it's still not finished. You know, there are other cathedrals in Europe that have been under construction for 800 years. So for this, we really have to take the long view. And an example that maybe is a little bit more closely tied to NASA is that the Apollo samples came back 50 years ago. And because of the fact that we have increasingly sophisticated analytical techniques that require smaller and smaller samples and can do more and more things, we're still getting exciting science from the Apollo samples. So here's an example from 2013 reporting evidence of water in lunar materials. A huge surprise. And so, you know, it's not just the samples, but it's the techniques and the instruments that really go into all the things that we do. In the case of these interstellar samples, we don't have very many of them. We don't know when we're going to get the next samples. And they are by far the rarest samples in NASA's collection, as I mentioned before. That means that if we're thinking about doing something that might pose a risk to the samples, like for example, one of the things that we need to do with these ultimately is to measure the relative abundances of the isotopes of oxygen in these samples, we cannot take risks or undue risks. Some amount of risk is going to be tolerable, but we really can't take major risks. We have to do everything we can to make sure that when we prepare these samples for analysis, that we don't ruin them, because it could be that the best techniques, you know, are 20 years in the future. Who knows? So it's a difficult balancing act that we have to carry out, and so it means that we might have to wait and wait and wait for the techniques to come around for us to be able to do this. So even though it's frustrating for people who are getting a little bit long on the tooth like me, we really have to take the view that these are precious, you know, national treasures that we have to be very, very careful with. So some of the lessons that we've learned. So I don't think I have to tell anybody here on this call about this, that this is not just education and public outreach. And not that I want to denigrate education and public outreach, but that's not the principal focus. When we started Stardust at Home, that was not our idea. Was, you know, the EPO part of it was really a great thing, but it was serendipitous. We turned to this approach out of desperation. We really didn't know how else to do it. And so, but I think that really is an important point, that the participants must know from the organizers of the project that they're doing something that's really essential and that can't be done in any other way. And that I think has really been key to our project. The work, of course, should have high granularity, so it's not something that, you know, you have to spend an hour at to make any progress at. It needs to be something that you can do in just a few minutes and still be productive, and the feedback should be immediate. The calibration was really important for us in a number of ways. As I said, we feed in these calibration images into the data stream at random with a frequency of typically something like 1 out of every 5 or 1 out of every 6 images. And this enables us to measure efficiencies of individual volunteers, and we can measure efficiencies and also their false positive rates. It also enables us to make scoring, and that's evolved over time. We now take a very different approach than we did originally. We have something called power scores, and I can talk about that in Q&A if you'd like. And this is very highly motivating for a lot of people, as I'm sure many of you know. It also is really important to have these calibration images in the data stream to keep attention. So when I was a grad student, I spent weeks looking for very, very rare events in nuclear track etch detectors, and I won't bore you with that story. But the challenge I had, you know, doing it by hand was that it was really hard to keep attention. So you'd think about lunch or whatever, and then something totally obvious would sail right past you. And so I had to scan these things like 3 times to find all the things that I was looking for. So when you're looking for rare events, having something that will keep your attention is really, really important. For us, there was also surprise about what kind of volunteers we had. So we very deliberately did not collect demographic data in order to avoid human subjects rules. But we've, of course, know a lot about many of our most active dusters. I mentioned Bruce Hudson, who's a retired carpenter. Many of our most productive dusters have turned out to be retired engineers, which maybe is not too surprising. A big surprise for us was we got a lot of Italians. Who knew? And they don't even know each other. But maybe it's because of a long history of doing science over centuries, you know, in Italy. I don't know. And they can't even tell me. They're just like, oh, I like doing this. So, okay, great. And I'll come back to one of those in a second. And I think the other thing is that we've had, unsurprisingly, partly because of the bottlenecks in the project in other ways, we don't have nearly as many people involved in this as we originally did, of course. But I think that's great, actually. I mean, I think it's fantastic that people are off doing fantastic science in all kinds of ways. So I don't view that as a bad thing at all. It's totally appropriate and actually to be expected. We early on, we had certificates that we used to hand out for people who'd gotten to different levels of accomplishment. We don't do that so much anymore, but that was motivating. We also recruited a bunch of our most experienced dusters to serve on a red team, which had privileges to be able to review and promote tracks and candidates. And several tracks were found by the red team that were missed in the general search. So this was really a great thing. And then I mentioned also this idea that you know, discoverers of particles, this was an agreement we had early on, would be co-authors on papers. So even though we've been going at this for 14 years, we're still making progress, and even recent progress. So I want to call out Augusto Arbizzone, who is from Palermo, and he participates on every one of our monthly third Thursday telecons on Stardust at Home, so one of our most dedicated Stardust at Home dusters. And he discovered a track several years ago that we finally got to analyze on the new cosmic beam line at the Advanced Light Source. And this is a particle that Augusto named Bianca after his late wife. So this is very sweet. And so this is an image of Bianca on the left. This is from an abstract by Anna Butterworth that was going to be presented at the Lunar and Planetary Science Conference in Houston, which of course was canceled. So this is the smallest track we found, particle we found in aerogel so far. And it looks yet different than the other ones that we found. And so it's underscoring the fact that there seems to be an enormous diversity in interstellar dust particles. And this is some X-ray spectroscopy of this particle that illustrates this difference. So the other thing that we've been turning to now is coming back to this idea of machine learning. And it's not so much to replace our dusters, but to support them. So Zach Gainsforth and a talented undergraduate named Logan Yeager here at Berkeley have been working on using a convolutional neural network to identify craters in aluminum foils in an efficient way. Now, this can never replace humans because humans always have to look at things. But what we want to try to avoid is having the Stardust at Home dusters look through thousands and thousands and thousands of completely empty images, because these are really rare, you know. So if we can throw away the ones where we're sure there's not a crater using this machine learning technique, then we can really ramp up the human efficiency and make that a little less boring, but also more efficient at finding craters. And so we're doing this in the foils, and we're also doing this for tracks in aerogel as well. And these are just some plots showing the training efficiency of these of the machine learning, which is now approaching more than 99% efficiency in detecting craters. Okay, I'm almost done. So I just want to say, you know, I don't think I have to tell everybody on this call that Stardust at Home and other citizen scientist projects demonstrate that this approach works for a very specific set of projects and problems. It's not a general approach. A lot of things, maybe most things, can really be approached using other techniques, but there is a very important niche that citizen scientist projects form. But you know, we're used to thinking about this as a very new kind of thing. It actually isn't. So it's not really novel, actually. So it turns out that in the dawn of the space age, the Smithsonian Institution started something called Operation Moonwatch that recruited observers and ham radio operators who were kind of the hackers of their day to monitor the first artificial satellites. And everybody thought that they were going to be American, but of course it was a huge shock to everybody when the first one was Soviet. One of those participants in our Operation Moonwatch was my dad. He went on later to Caltech and then was principal investigator on the first wide field camera for Hubble. But this was formative for him, this Operation Moonwatch. And it's funny that I didn't even make this connection until years after we started Stardust at Home and realized, oh yeah, of course. But it was not in my mind when we started the project. And his favorite phrase is, if you're not having fun, you're not doing it right. And I take that to heart. So I just want to summarize here. This was our view of comets in 1577. This is a great comet of 1577, a woodcut. This is our view of comets in 2015, a particle called Cecil, where we're able to practically see individual atoms. So it's about a 19 order of magnitude improvement in spatial resolution. But for interstellar dust, it's even more stark. Our understanding of interstellar dust has, up until now, come from astronomical observations through telescopes of interstellar dust. But now we think we're seeing individual interstellar dust grains in the laboratory. I think it's about a 23 order of magnitude improvement in spatial resolution. It's hard to beat that. So I'll stop here.